So hello, Chem 2, and welcome to what I believe is the sixth video for Chapter 3, talking about all the concepts of stoichiometry. This one, we're going to focus a lot more on some applications of what you can do with stoichiometry. So this is going to be kind of an interesting one. I'm going to do three separate problems that have a real life, real science, real chemistry life situation, and see how we can incorporate what we've already learned in the previous videos for those problems. So, already done the mole, already done mass relations, and now we're doing it reactions. And again, we're talking mostly about applications. So we're going to show how stoichiometry can be used in common chemistry applications. So that's our flow chart, and we're going to still use this, sort of. We're still going to use the concepts from this, but we're going to stretch out a little bit in regard to applications. For the seventh video of the series, we're going to actually focus on one very, very important application, and that is a combustion analysis application, a very, very common application. But the problems we're going to do today are going to be ones that are going to be a little more complicated, a little more interesting, and the last one is really, really complicated. So let's take a look. First one, you have an impure sample of zinc, which means you have a sample of some rock, some chunk that has zinc in it, but it's not only zinc. Some of it is something else. Okay. When you react it with hydrochloric acid, the zinc creates zinc chloride in hydrogen gas. So first question says, we'll write the balance equation for the reaction that you're seeing take place. And second, if you obtain 0.0794 grams of hydrogen gas during this reaction from a 3.86 gram sample, remember that sample is not pure, has a portion of it is something else. Calculate the purity or the percent purity of the sample. And then the last question says, what assumption must be made for part B? And the main assumption we're going to make here is the fact that the other things, the impurities in the sample, do not react with the hydrochloric acid to produce any type of gas. So we don't want to have a contaminated gas and have some of that gas be something else. So all of the gas that you collect, the hydrogen gas you collect, is going to all be from the reaction of the hydrochloric acid and the zinc. So let's get started. So the first part of this problem is pretty straightforward. We need to write a balanced equation. So we know we have, let's see if my pen will work. Where are you, pen? There it is. So we have zinc plus hydrochloric acid giving us zinc chloride and hydrogen gas. And I can already tell I need a 2 here because I have 2 hydrogens and 2 chlorines on the right-hand side. So that's my balanced chemical equation. So in this reaction, we're going to start with some amount of hydrogen gas here, and it says we reacted. I'm looking at my notes so I get all the numbers right. 0.0794 grams of hydrogen gas gets made. Okay, and it wants to know the purity of zinc. So here's the way I look at that. If I've got a piece of rock, my rocks all look like blocks, and some of it is zinc, and some of it is not zinc. If I can figure out how many grams of zinc was needed to react with the hydrochloric acid to make my hydrogen, then I can figure out what percentage of the whole rock was zinc. So I'm going to do that. I'm going to take 0.0794 grams of hydrogen and find out how much that is, how much zinc I needed. So 2.01588 grams of hydrogen gas for every mole of hydrogen gas. In my balanced equation, it's a 1-to-1 ratio, so I have 1 mole of zinc for every 1 mole of hydrogen gas. And if I look up zinc on the periodic table, I get that zinc has a molar mass of 65.39, at least on the periodic table that I have available to me. That means In order to create 0.0794 grams of hydrogen, I needed 2.58 grams of zinc. So how pure was my sample? Well, I had 2.58 grams of zinc in a 3.86 gram sample. I times 100 to give me a percent, and I find out that my sample was 66.8% zinc. Application. Using our mass to mole to mass concept to take it one step further and determine the percent of zinc in the sample. Okay, example number 2. I have a sample of lithium and a sample of nitrogen, and I happen to have 5 grams of each. I have 5 grams of lithium and 5 grams of nitrogen gas. And I let them react. And I want to know how much lithium nitride is going to be made, not theoretically, but knowing that I have an 80% yield. Okay, so I've got a little bit going on here. I've got the reaction. I know 2 reactants, and I know that when I'm done, I'm going to have 80% yield. So I want to first figure out what theoretically I should have. So let's see. I'm going to go down. So I'm going to start with a reaction. I've got lithium plus nitrogen to give me lithium nitride. And I need a 2 here to get the nitrogen's balance, and I need a 6 here to get the lithium's balance. So I've got a 6:1:2 ratio in my coefficients for the balanced chemical equation. Now I have 5 grams of both of my reactants. So I have 5 grams of, one second, I have 5 grams of lithium, and I have 5 grams of nitrogen. So I'm going to find out how much of the lithium nitride I could make, starting with 5 grams of each. So for the lithium, I'm going to divide by the molar mass of lithium. So I have 6.941 grams per mole. That's for lithium. I know that if I look at my balanced chemical equation, I'm going to make 2 moles of lithium nitride for every 6 moles of lithium. And if I did this right, and I made a mistake on this problem, so it's very possible I made a mistake somewhere along the way, but bear with me. I got 34.8297 grams of lithium nitride per mole of lithium nitride. So if lithium was my limiting reactant, I could make 8.36 grams. What if nitrogen is my limiting reactant? Well, I'll do the same thing. Walk my way across. Nitrogen's molar mass is 82.0134 grams per mole for nitrogen. My molar ratio for nitrogen is for every 2 moles of lithium nitride, I only need 1 mole of nitrogen. And I still have the same molar mass, 34.8297 grams per mole. So if nitrogen were my limiting reactant, I could make 12.4 grams of lithium nitride. So I know that lithium is my limiting reactant, and this is my theoretical yield. Okay, so I know that percent yield is equal to actual or experimental divided by theo. That means my percent yield times 100 divided by 100 times my theoretical yield is going to be my actual. So percent yield was 80.5 out of 100 times 8.36, which means if I were 80% effective or 80.5% effective, I would have created 6.73 grams of lithium nitride. Okay, so utilizing, again, mass to mole to mole to mass, but now adding in, not asking for the limiting reactant or asking for the percent yield, saying, I know that this reaction is only a certain percent effective. How much would you make if it was 80% effective? Okay. Now, finally, the last question, and I almost hesitated to add this one because it's pretty complicated. It takes a higher order of thinking. It takes some real algebra skills to do this, so much that I'm going to say there's a chance that I may have made a mistake along the way. I checked my work. It makes sense. The numbers make sense. But I'm just going to tell you that there's a possibility that there's some challenges along the way. And I'm actually going to try to do this in such a way that's going to simplify some of the numbers. So kind of throwing some of the precision factors out the window so that the concept of how to do the problem might be a little easier. So I have two substances, copper sulfate and magnesium sulfate. And I have this container that has both of them in it. And I don't know how much, but I'm just going to put them in different quantities so I know that they're not going to be exactly the same. Okay? I know this mixture has a total mass of 5.02 grams. I also know that when I heat this up and drive off all the waters, I get rid of these waters and I get rid of these waters. When I dry this up, my new mass is 2.988 grams. Question is, what is the percent of copper sulfate by mass in the mixture? Okay, so let's start gathering some information. First thing, I have two compounds. I have copper sulfate and I have magnesium sulfate. I know I'm going to need these, so I calculated them. My molar mass of copper sulfate is 249.685 grams per mole. My molar mass of magnesium sulfate is 246.475 grams per mole. So if I have both these numbers, I'm going to need them. I know that. Okay. I know that I started the mass of the mixture was 5.020 grams. I know the mass of the salts was 2.988 grams. What that means is I drove off 2.032 grams of water. The difference between those two numbers is the number of grams of water total that I have here. So I realize I have two things I don't know about. I don't know the amount of copper sulfate and I don't know the amount of magnesium, but everything seems to be blended together. So in my mathematical mind, I think this might be a system of equations. So let's make this a little easier. Let's use X and Y. X I'm going to define as being the moles of the copper sulfate. And Y is going to be the moles of magnesium sulfate. Okay, now you're going to see where this plays a role in a second. So first thing I'm going to do is going to set up an equation about the mass of the mixture. I know the mass of the mixture was 5.020 grams. I know that's a combination of the mass of the copper sulfate and the mass of the magnesium sulfate. So the mass of copper sulfate is going to be the molar mass of copper sulfate times the number of moles of copper sulfate I have. The mass of the magnesium sulfate is going to be the mass of the molar mass of the magnesium sulfate times the molar mass, or sorry, the number of moles of magnesium sulfate. Second equation, what about the mass of the water? Okay, so the mass of the water is 2.032. That's going to be equal to the molar mass of water, 18.0153, times, we'll call it Z, which is the mass of water. Sorry, moles of water. But wait, we know that moles of water is Z is equal to 5 times X plus 7 times Y, because in every X number of moles of copper sulfate, there's 5 waters. In every Y moles of copper sulfate, there are 7 waters. So Z happens to be 5X plus 2Y. Okay. We do one more extraction here. So next thing I need to do is I'm going to take this equation here and I'm going to distribute the 18.153 across both of them. I'm going to do that on the next page. Okay. So let me do this. So I'm going to rewrite it. 2.032 equals 18.0153 times 5x plus 7y. And I'm going to distribute the 18. So I get 2.032 equals 90.0765x plus 126.107y. I just distributed the 18.0153 across this equation. So now I have essentially two equations and two unknowns. I have the original equation that has, let me go to the previous page, that is right here. And I have the new equation. So let me rewrite that original equation. I have the 5.020 equals 249.683 x plus 246.47 y. So I have two equations and two unknowns. So I have what I'm going to use as systems of equations. Okay. Now what I'm going to do is I'm going to take this first equation and I'm going to solve it for y. To solve it for y. So I get 2.032 minus 90.0765x equals 126.107y. I literally just pushed the 90 to the other side. Then I'm going to divide both sides by 126.107. So I'm going to get, if I did this right, and this is where I say the math might not work out 100%, but I checked my answer, at least I gave an answer that made sense. I get 2.032 divided by 126. I get 0.01611 minus 90 divided by 126, I get 0.714x equals y. Now, why is that important? I'm now going to take this formula and I'm going to insert it into this one. I'm going to multiply through and insert this x in for y, so this portion in for y. So I get 5.020 equals 249.683 x plus 246.47. I think there's more to that, but I'm okay. Times 0.01611 minus 0.714x. I'm going to distribute that across, and I get 5.020 equals 249.683x plus, so I got my numbers right, 3.971 minus 176x. Now, I lost some sig figs here, but the numbers work out. Okay, so now I'm going to need to solve for x. So I'm going to push this to the other side. I'm going to subtract 3.971 from both sides, and I'm going to get 1.049. And then I'm going to combine these two together, and I'm going to get 73.68x. Okay, so it's time to solve for x. So if I just had 1.049 equals 73.68x, x is going to be 0.0142. That means that I have 0.0142 moles of copper sulfate. So how many grams of copper sulfate do I have? Well, I'm going to take my molar mass, 249.685 times 0.0142, and I find that I have 3.546 grams of copper sulfate in my original sample. What percent of the original sample is that? 3.546 divided by, what was the number? 5.020 times 100. My original sample was, and I didn't do this math. I didn't answer the actual problem. Okay, let's check to make sure my math worked. Of 3.546 divided by 5.020 times 100. I got that my sample was 70.6% copper sulfate. Now, I just wanted to make sure that I did this right. So what I did was I went back and I put into my equation that I solved for y, for x, I put in my number of moles, which was 0.0142. And I got that y turned out to be 0.00597 moles. That was the moles of magnesium sulfate. So I wanted to see whether my math worked. So this is the answer. I'm just checking my work now. Let's see whether my math worked. So I solved for the mass of magnesium sulfate. And I did the 473.75 times 0.00597. And I got my mass to be 1.471. So if I add together my 3.546 to my 1.471, I got that I had 5.017 grams. I am happy with that. Yes, I'm off by 3/1000ths of a gram. That's probably where I dropped that one sig fig along the way, but I'm happy with the numbers. So this systems of equation concept is going to show up a lot along the way. I want you to see how your algebra skills that you learned can be used in the chemistry classroom. Okay, I want you to see how your algebra skills can be used in the chemistry classroom. It requires a little bit of thinking outside the box. It needs a little bit of conceptual understanding. But like I said, these are application problems. How do we use this concept of the mole that we've developed to look at more complicated, higher order problems? In our next video, we're going to focus on the last and probably the most common application of stoichiometry, and that is the combustion analysis. So until next time, stay safe, practice that social distancing, and toodles.